Good morning, everyone. Okay, so we're going to start off with warm-up, as we normally do. So what I need you to do is go to the warm-up section of your binder and have you do these 4 questions. Okay, those of you watching at home, please do pause and then come back for the solutions once you have done this on your own. Again, if you're not doing this on your own and just waiting for the answers in the video, you're not really helping yourself. Okay, welcome back. So you've done this in your binder and you are now checking your answers. Okay, so x plus 6 times x minus 6. I'm just going to do the first one out completely, then I'm just going to run through the answers for the other one. So that's going to be x squared minus 6x plus 6x minus 36. Okay, we have like terms over here. Negative 6, positive 6 makes 0. So our answer is just x squared minus 36. Okay, number 2, you should have had x squared minus 1. Number 3, you should have had x squared minus 100. All right, so number 4, what did you notice? Well, what I was looking for here was for you to observe a pattern. So you had, in number 1, we had a positive 6 and negative 6, right? Number 2, a positive 1 and a negative 1. Number 3, a positive 10 and a negative 10, okay? When we multiplied, these are called conjugates. Multiply conjugates. The middle term cancels. Okay, so negatives, this number 1 gave us a negative 6 and a positive 6 for the middle term, cancels out because it makes 0, all right, etc. And same thing for 2 and 3, right? So we got our answers. If you take a look at, let me just circle our answers. So conjugates give differences of perfect squares. Okay, and you probably came up with something more in your own words, all right? Probably didn't know what a conjugate is, but again, all a conjugate is a number and its opposite, like positive 10, negative 10, positive 6, negative 6, etc. So when we multiply those together, we get a difference of perfect squares. And I want to go right into the notes and define what perfect squares are. Okay. So perfect squares are like, well, 1 is a perfect square because 1 is equal to 1 squared, right? 4 is a perfect square because 4 is equal to 2 squared. Let's skip ahead. 25 is a perfect square because 25 is equal to 5 squared, all right? Let's see, 121 is equal to 11 squared. 225 is equal to 15 squared, all right? And you know how if you go to the calculator and you do like square root of 3, you're going to get 1.8 blah, 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 right? 3 is not a perfect square because its square root is 1.8 and then a whole mess of decimals. But if we take the square root of 225, we're going to get exactly 15, okay? That's what a perfect square is. Okay, so they're those numbers that have clean whole number square roots. All right. So let's go back. So difference of perfect squares. If we have something squared, all right, A here is just any number, b here's any other number. If we have something squared minus something squared, again, difference, it's going to factor as a plus b times a minus b. Let's quickly prove that. If we multiply out, that's a squared minus a times b plus a times b minus b squared. And then notice the ab terms drop out. That's a squared minus b squared. Okay? Where a and b are perfect squares. All right? And again, because their differences of perfect squares, they must be separated by subtraction. All right? If you have the sum of perfect squares, if you have something squared plus something squared, it's not going to work. All right. Let's take a look at a bunch of examples to clarify. So x squared minus 9 is a difference of perfect squares. Here's why. Because x squared minus 9 is parentheses x squared minus parentheses 3 squared. Okay? So that means this is going to factor as x plus 3 times x minus 3. All right? So the a in our formula over here, a is x, b is 3. All right. Number 2 is the same thing, but it's backwards. Okay? So the 9 comes first. That's really 3 squared minus parentheses x squared. So a is 3, b is x. That's going to factor as 3 plus x times 3 minus x. Okay? And the order depends what you start with. Okay, number 3, 225 minus y squared. Yes, that's a difference of perfect squares because 225 is really 15 squared minus parentheses y squared. So a is 15, b is y, so that's going to be 15 plus y times 15 minus y. And again, when you're factoring, anytime you're factoring, you can always check by multiplying back out. Okay. Number 4, slightly different, but if we take a look, the first term, how can we write that as a perfect square? Well, we have a 4 and an x squared, okay? So 2 is a perfect square, x is a perfect square, squared, like that, minus 36, so that's going to be 6 squared. So a is equal to 2x, b is equal to 6, so that means we have 2x plus 6 times 2x minus 6. All right, number 5, 16x squared minus 9. Okay, so 16 perfect square, so that's going to be 4. X squared perfect square, x, all squared, minus 3 squared. So the a is going to be 4x, the b is going to be 3, so that's going to factor as 4x plus 3 times 4x minus 3. Number 6, 81a squared minus 49b squared. Okay, so 81 is going to be 9 squared. A squared is going to be a squared minus 49, so that's going to be a 7 in the parentheses, and we're going to need a b in the parentheses. So a is going to be 9a, b is going to be 7b. That means we're going to have 9a plus 7b times 9a minus 7b. All right. Number 7. What you should notice hopefully right away, if you're paying attention, is this. This is not a difference of perfect squares. So the answer to this is trick question, can't do, all right? So the correct mathematical way to write it is that it's prime. Can't factor, okay? Again, this only works if you have differences of perfect squares. Because yeah, 25x squared is a perfect square, 16y squared is a perfect square, but it's not a difference of perfect squares. Okay, last one, 4y squared minus 64. Okay, so 4y squared, yeah, we can write it as 2y squared minus 64, so that's going to be an 8 squared. So a is going to be 2y, b is going to be 8. So that'll factor as 2y plus 8 times 2y minus 8. Okay. So we've gone over several factoring techniques, GCF, factoring ax squared plus bx plus c, and then factoring differences of perfect squares. Now what we want to do is use factoring to start solving some quadratic equations. So we've just factored expressions so far, and now we're going to start solving quadratic equations, which you learned last year, and again, this is, just starting out with review, but important. Okay, what I want to do in this table, we're going to compare and contrast linear equations to quadratic equations, so we're clear on the differences. Okay, so linear equations, look like 2x plus 5 equals 11. 3 times x plus 1 equals 4 times x plus 2, etc. Okay? That's a linear equation. Quadratic equation would look like x squared plus 3x equals negative 10. 2x squared plus 7x plus 10 equals 0. Okay? So methods to solve. Well, actually, let's go back a second. What you should notice, linear equations, the degree, the highest exponent is always 1, right? All these x's are understood to have 1s for their exponent. For quadratic equations, what makes a quadratic equation is degree is 2. Degree means the highest exponent, okay? And what you should also remember is usually quadratic equations are set equal to 0, right? Like this example. So methods to solve. How did we solve a linear equation? We used inverse operations. All right, so like in this equation over here, we would of course subtract 5 from each side. On this equation, of course, we distribute out, get rid of the parentheses, and then subtract things from each side. You know the drill. For quadratic equations, we solve by factoring. For now, you also learned a few other methods last year, like the quadratic formula, that big formula with the square root in it that you hopefully remember. We also learned completing the square and a little deeper will go this year, okay? All right, so there's factoring and there's others, but we just need factoring right now. Number of solutions. What you should remember, linear equations can have none. Sometimes you get no solution, and sometimes you get, well, not sometimes, most of the time you get one solution, and then you also have the case where you have infinitely many solutions, okay? Quadratic equations can have no solutions. What we're going to say is they have no real number solutions. They can have another kind of solution called imaginary solutions that we will be getting into probably about a week or two from now. They can have one solution, or they can have two solutions. All right. So, comparison between linear equations and quadratic equations. Okay, so what I want to do next is review how to actually solve a quadratic equation by factoring. So a factorable quadratic equation. Not all are. All right. Many times, or most of the times, you're not going to be able to factor a quadratic equation, so that's when you'd use the quadratic formula or completing the square. So your first step in solving a factorable quadratic is set the right side of the equation equal to 0. All right. So if you look at these two over here, the bottom one is already set equal to 0. The top one is not. So you would, of course, want to add 10 to both sides to make it set equal to 0. All right. Step 2, factor the left side. And then step 3, we're going to use what's called the zero product property. Set each factor equal to 0. And then step 4, you're going to have two resulting mini equations, just really short linear equations to solve to get your solutions. Okay, let's take a look. Number 1. All right, notice number 1 only has only has 2 terms. All right, it's already set equal to 0, but since it only has 2 terms, we're not going to use ax squared plus bx plus c because there is no c term. So what there is it does have a GCF. And that GCF is 3x. So we're going to factor. This is going to be 3x times x minus 4 equals 0. All right, so we set the right side of the equation equals 0. We factored the left side. Now we're going to use the zero product property. So we're going to set each factor equal to 0. So one of your factors is 3x. I'm going to draw a line between factors. I'm going to write 3x equals 0. Your other factor, x minus 4, I'm going to write x minus 4 equals 0. Okay, so step 3, we set each factor equal to 0. Step 4, we're going to solve the resulting mini equations. So, of course, divide each side by 3. That means x is 0, plus 4 to both sides. So x is 4. So this first one has 2 solutions. They are 0 and 4. Okay, number 2, this one is not set equal to 0. So first we have to add 36 to each side, which gives us y squared plus 13y plus 36 equals 0. Okay, now that we have it set equal to 0, we're going to factor the left. So we need factors of 36, 36 and 1, 18 and 2, 12 and 3, and 9 and 4, and 6 and 6. So we need a pair that multiplies to 36, which of course these all do, and adds to the middle term. The one that's going to work here is 9 and 4 because 9 plus 4 will give you 13. And everything is positive on the left side. So this is going to be y plus 9 times y plus 4 equals 0. Now we'll use our zero product property. We'll separate the factors, set them equal to 0. Okay, and solve these little equations. So y is equal to -9, and y is equal to -4. Okay. Number 3. Number 3 is not set equal to 0, so we're going to want to subtract x from both sides. So we have x squared minus x minus 30 equals 0. Make sure you write it in that proper order. So now let's factor the left side, looking at factors of 30, 30 and 1, 15 and 2, 10 and 3, 6 and 5, and 7, 8, 9, nope, that's it. Okay, so we want a pair that's going to multiply to 30, -30, and add to -1. The pair that's going to do that is the 6 and 5. If we have a -6 and a +5, -6 plus 5 is going to make the -1, and then -6 times 5 is going to multiply to the -30. So that's going to be x minus 6 times x plus 5 equals 0. Let's use the zero product property. X minus 6 equals 0. X plus 5 equals 0. So x is 6 over here, and x is -5. Okay, number 4, excuse me. Number 4, we only have 2 terms, but you should notice that this looks like what we did today, right, with difference of perfect squares. Okay, so it's already set equal to 0, so we only have to factor. So that's going to be 10 plus 5y, 10 minus 5y equals 0, right? Use the zero product property. Um, 5y equals -10. So y is -2. So, and y is +2. Okay? All right. Number 6. So number 6 is not set equal to 0, so we're going to need to subtract 9 from both sides. So that's 2x squared minus 3x minus 9 equals 0. Okay, so factoring this one is a little more complex. We're going to look at the factors of 3, which is either 9 and 1 or 3 and 3. And of course, we have a 2x squared over here. So our factors are going to begin with 2x and x instead of just x and x. Okay, so let's try this pair. Remember, it's trial and error, but looks to me like the 3 and 3 is going to work better than the 9 and the 1. So I'm going to put in a 3 over here, a 3 over here. I know that if I do, that would give me a 6 if we had a plus, and then the -3 over here would give me a +3. So let's make this 3 negative, okay? And then let's make this 3 positive. So that's going to be 2x, let's check our factors, minus 6x plus 3x. Yeah, there's our -3x minus 9, -3x, perfect, equals 0. Okay, now that we have it factored, 2x plus 3 equals 0, x minus 3 equals 0, 2x equals -3. So x is going to be negative 3 over 2, and x is going to be 3. Okay. Last question. All right, well, this is going to be our easiest one because it's already set equal to 0. It's already factored. There's nothing, you know, the longer parts of this are already done for us. So all that's left to do, take your zero product property. 4y plus 3 equals 0. 2y minus 1 equals 0. 4y equals negative 3. So y equals negative 3 over 4. 2y equals 1. So y is 1 over 2.